Hi and welcome back to this segment where we're continuing with our study of matrix inversion. So in the last video we said that if a matrix is invertible, we refer to it as a singular matrix. Then a matrix which is not invertible, a matrix which is invertible, we refer to it as a non-singular matrix, while a matrix which is not invertible, we refer to it as a singular matrix. Okay. We say that we emphasize the fact that matrix inversion is defined for only square matrices, okay? And then we'd like to also add a note to that by saying that it is defined for matrix for only square matrices, because generally we say that if we have a matrix A and then we have another matrix B, if B is the inverse of A, B is the inverse of A, written as that, if A times B is the same as B times A, and this should give us the identity matrix if these are of order n by n, n by n, and then this is of course the identity matrix of order n. So this condition here, okay, is going to rule out matrices which are not squared, because you cannot have A times A inverse is not going to be equal to A, won't be equal to A times A inverse if A is not square, okay, i.e. these will most likely not be conformable for multiplication. Okay, so now here we would like to look at a special case of a 2 by 2 matrix. If A is a 2 by 2 matrix given with the entries A, B, C, and D, then we are going to get the determinant. Okay, we shall, for now, okay, we assume that we don't know the determinant, but for now, okay, we don't know the determinant, but for now let us, okay, we shall later on call this delta the determinant, but we shall compute these properties of the matrix which include determinants and so on later on. So let us assume that we don't know anything about the determinant and we just call this delta. This delta, you're simply going to get the product of the entries on this main diagonal, i.e. you're going to get A multiplied by D, and then you subtract the product of the entries on this minor diagonal, the one in B, and that is B times C, okay? And if this is non-zero, i.e. this is not equal to 0, then we shall say that if delta given by the product of the entries on the main diagonal minus dot on the minor diagonal, this is the main and then this is the minor, okay, then we shall say that A inverse is simply going to be given by 1 over delta, and then the entries on the main diagonal, you interchange them, and then we change the sign of the entries on the minor diagonal. So we are saying that these ones here on the main diagonal, they change, okay, and then the ones on the minor diagonal, these ones switch positions, and then these ones here change signs, okay. So this is our A inverse, okay. Yeah, so when we come up with the next example, you can put in the figures here, but generally this is it here. What else? We say that although not all matrices are invertible, when an inverse exists, it is unique. So we shall say that the inverse is unique. Okay, it is the proof is quite easy. It follows from the one which we just saw at the introduction here, when we are trying to prove that if we have x1 and x2, solutions to the equation alpha x equals to beta, then we show that x1 equals to x2. So here we are going to continue and then say that in the same fashion, if now x1 and x2 are both inverses of a non-singular matrix A, i.e. If A inverse equals to x1 and also A inverse equals to x2, okay, then if then we can write that x1, okay, equals to x1 times the identity, because x1 times the identity still remains x1, okay. When you multiply by the identity, you don't change the result. Equals to x1, but since we said that x2 is also the identity, that means that we can, instead of writing the identity, we can write it as the product of A times x2, okay. And then we know that now associativity can come in, and then we can say that this is x1 times A, okay, then times x2. Again, since we know that x1 is the inverse of A, we know that the inverse multiplied by the matrix is going to give us the identity. Then we have times x2, and then we know that the identity times x2 is still x2, and therefore we come up with our result that x2 is equal to, x1 equals to x2, okay. Yes, so what else here? Matrix inversion is so in this way we have defined it analogously to scalar inversion, what we did at first, okay. And since matrix multiplication is associative, we have used all this reasoning here in trying to show that x1 equals to x2. Okay, therefore we are going to have some of the following properties. Let us come up, we are going to write these properties here. So now, if we have a matrix here of a system, let's say A of a square matrix there, and then we have this vector of size n by p, okay. If this equals to b, of course by now we know that the size of b is going to be of order n by p, okay. Then the solution, we can get our solution x as A inverse multiplied by b, that is if the inverse exists, okay. By defining it analogously to scalar multiplication, where we say that alpha times x equals to beta, and we say that the solution to that is alpha inverse times beta, okay. It's the same idea here. So we are going to say that a system of n equations in n unknowns, which what we have just written here, can be written as a single matrix equation. Okay, maybe we can say that we can write it as a single matrix multiplication by saying A x equals to b. Of course, this is n by n, and then this is n by 1, okay, and then this is n by 1, whose solution x, okay, whose solution x is going to be given by A inverse times beta. So it is important to note that the representation of A inverse times b, I said beta previously, the representation of A inverse times b, okay, is mostly notational or just theoretical here. However, in practice, the systems of equations given by ax equals to b are rarely solved by first finding the inverse, that is A inverse, and then multiplying it by b. Why is that so? Because later on we shall see that the process of first finding the inverse is computationally expensive. It involves quite many operations, especially if the matrix is very huge. Okay, so we shall later on see other techniques which people can use to solve these systems of equations ax equals to find the solution x without having to first find the inverse and then multiply it by the right hand side vector. Okay, so now we would like to conclude this section here by saying that if the inverse exists, okay, if the inverse exists, then if the inverse exists for an n by n matrix A, okay, then the following statements are going to be equivalent. Okay, of course the inverse exists. We have said that the inverse exists. Okay, and we say that if the inverse exists, this matrix is non-singular. Okay, then okay, we talked about rank in our previous matrices. So here we find that the rank of the matrix, the rank of A should be equal to n. Remember, n by n is the dimension. Okay, so the rank, the number of non-zero rows, okay, in A after reducing it in row echelon form should be this given by n. Okay, and then we can carry out this operation. We can use a Gauss-Jordan, reduction of the rows of A to come up to the identity. Okay, we shall later on see we can use the Gauss-Jordan to transform the matrix A to the identity matrix I. Okay, and then later on we say that ax equals to 0 if we have this homogeneous system. Therefore we have that x should be equals to the 0 vector. Okay, the proofs are not important for us at this stage. We are simply supposed to know just these properties here, and then we shall use them in the next section.